In this laboratory activity, we explored the design and implementation of finite impulse response or FIR filters using Python. The main objective of the experiment were to create FIR filters programmatically, apply them to a noisy signal, and analyze how the filter behaves both in the time and frequency domains. FIR filters are digital filters whose impulse response lasts for a minute duration. They operate only on the current and past input samples, which makes them inherently stable and capable of providing linear phase characteristics, an important feature in many signal processing applications. To begin, we reviewed the basic FIR difference equation, which relates the input signal, output signal, and the filter coefficients. These coefficients define how the filter behaves and determine which frequency are passed or attenuated. For this activity, we use Python along with three main libraries: NumPy for numerical operations, SciPy for signal processing functions like filter design and filtering, and Matplotlib for plotting. If the required libraries weren't installed, we could easily add them using PIP, ensuring that our environment was ready for implementation. The first step of the code involved generating a test signal. We created a 1-second signal sampled at 1000 Hz that contained a 50 Hz sinusoid. A 200 Hz sinusoid will have amplitude and other random noise. This gives us a mixed noisy waveform from that we later filtered. After plotting this raw signal, we designed low-pass FIR filter. Using the Hamming window method, the filter had a cutoff frequency of 100 Hz and consisted of 51 coefficients. Using SciPy's sphere width function made the design simple, and visualizing the filter's frequency response allowed us to clearly see how frequencies above 100 Hz were expected to be attenuated. Once the filter was designed, we applied it to the noisy signal using the filter function. When we compared to the original filtered signals in the time domain, it became easy to see how the high-frequency components were deducted, while the low-frequency sinusoid remained dominant. This demonstrated the filter's effectiveness in cleaning up to the signal. Finally, to further understand what was happening in the frequency domain, we used the fast Fourier transform FFT to generate magnitude spectra for both the noisy and filtered signals. These plots showed a clear difference that 200 Hz frequency peak was significantly reduced after filtering, while the 50 Hz component remained strong. The confirmed that FIR low-pass filter successfully performed in its intended function. In conclusion, we were able to design and implement an FIR filter using Python, while gaining a practical understanding of how filter parameters influence performance. Applying the filter to a noisy signal visually demonstrated how high-frequency noise can be suppressed while preserving important signals components. Analyzing the filter's frequency response and FFT results helped verify that the filter met the expected design goals and behaved correctly in both the time and frequency domains.